Kia ora Year 12. I'm going to start doing some revision videos for integration, and this first one is looking at how we can integrate some exponentials. And it's going to revise integration by parts and maybe integration by substitution. I'm going to do 3 of these videos tonight. So what I want you thinking about here is when you look at an integral, how do we decide whether it's a really easy one or one that needs substitution or one that needs parts? So these 3 integrals here have got one that is a very easy one and 2 that are going to need integration by parts. And in one of them, the integration by parts is going to be as straightforward as it gets, and in another one it's going to be a little bit trickier. So just have a go at them first and see if you can work out which one's which. Okay, so let's start looking at the first one. So when I look at that, here's what I think about. I look at the e to the power of x, and I think about what the derivative of that is, and it's e to the power of x. So this x sitting here is not going to help me. In fact, it's going to make things more complicated. This is a good candidate for integration by parts. What I'm looking for when I do integration by parts is to take a product and to split it into 2 bits. One bit that we can integrate and one bit that we can either leave as it is or differentiate. And what I'm looking for when I differentiate is to have the thing simplified down. Okay, so in this case here, I'm going to choose the e to the power of x to be the bit that I integrate each time, and the x will be the thing that I either leave or differentiate. So to do this first one, we start by writing it out, and then I leave the x alone and I integrate the e to the power of x. Then I subtract the integral of 1, which is the derivative of x, times e to the power of x dx. That gives me x times e to the power of x minus e to the power of x plus c. So when you're working with integration by parts, some of you might want to use this kind of a table over here, where we decide what do we leave and differentiate, and what do we integrate and integrate. And you can even write those derivatives and integrals out underneath it if you want to. So that leaving it will be the x, the differentiating it will be the 1, and then the integral of e to the x stays as e to the x. Okay, so over here, going over it one more time, this x is what we decided to leave, and this e to the power of x is the integral of this thing in here. Then we subtract the 1, right, which is what we differentiated, times e to the power of x. And you can see that what we're trying to get here is that this integral is simpler than the one we started with. With integration by parts, you can always check it back by differentiating your answer, but I'm not going to do this here. Okay, let's have a look at the second one, which is this integral. Again, the first thing that I'm going to check is that I've got e to the power of x, and its derivative is e to the power of x. So this x squared here is going to make things worse. So it's a good candidate for integration by parts. We've got x squared times e to the power of x dx. If I integrate this, it's going to stay as e to the power of x. And if I leave or differentiate this, it's either going to stay the same or get better. So the x squared is what I'm first going to leave and then differentiate. So here, what we want to do is to leave the x squared as it is and integrate the e to the x, then take away the integral of 2x, right, so that's differentiating the x squared, times e to the x dx. So now we can take a look at this one, and we see that this is still not great. So we have to do integration by parts a second time. So we'll have x squared e to the x minus we're going to leave or differentiate this and integrate for e to the x. So it's minus 2x e to the x minus the integral of 2 e to the x dx. Sometimes we have to do it 3 times, but not usually. Here we've got x squared e to the x minus 2x e to the x plus this very easy integral here. That gives me a final answer of x squared e to the x minus 2x e to the x plus 2 e to the x plus c. So that's the first two done. Now both of those used integration by parts, no substitution so far. Let's have a look at this last one and see if maybe this is the one I said might be the easy one. And it is. Now the reason it's the easy one is because here I've got e to the power of x squared. So to differentiate that I need to use the chain rule. And the derivative of x squared is 2x. Now we haven't got 2x, but we've got the x sitting here. So that tells me that I can do this one using reverse chain rule. I can either do it in my head or I can do it using substitution. So I'm going to show you both ways now. So first of all, just looking at it, let's try something, leave a gap. It's going to be something e to the power of x squared. Now when I differentiate that, I'm going to have 2x sitting out here, but I just want x. So we have to multiply it through by a half. So that's my answer. So we can do that by inspection once we're confident. But if we're not confident, we can do it using substitution. And there's lots of substitution work in Delta, and there's lots on Dr. Frost. So let u equal x squared. Du by dx is equal to 2x. So du is equal to 2x dx. You can see in here we've got x dx. So 1/2 du is equal to x dx. That means that we can rewrite our integral in terms of u completely. So we're going to have 1/2 times e to the u du. And that equals 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. Okay, so that's the first video. The next one's going to have some examples that mostly have got the natural log in them. And then the third video is going to be more challenging and it will have a combination. Thanks for watching. Make sure that you've worked through these questions once now with the video and then save them to come back to later on.